You know when you hit the shuffle button on your music player and you wonder if that next song is really a surprise? Or maybe you've used a password generator and just trusted it to create something truly unguessable. We bump into randomness all the time in our digital lives, but it turns out when a computer's involved, there's a pretty amazing illusion going on. And to get it, we need to ask a really simple question.
So is it? When your computer shuffles your playlist, is it basically pulling song titles out of a hat with no rhyme or reason at all? Or is there a method to the madness? The answer to that question, well, it gets to a huge challenge right at the heart of computer science. How can a machine that's built to be perfectly predictable create something that's totally unpredictable?
To really get how computers are faking it, we first have to take a look at the real thing. I mean, genuine, pure randomness. And as it turns out, it's literally all around us. The universe itself is just humming with randomness. That unpredictable crackle of old TV static, the decay of a single radioactive atom, even the subtle variations in atmospheric noise. These are all sources of what we call true random numbers. We can actually measure this natural, unpredictable noise to generate a sequence that has absolutely no underlying pattern. None.
And that's the key right there. Scientists have a name for this, a non-deterministic process. It's just a fancy way of saying that no matter how much you know about what came before, you have absolutely zero chance of predicting what comes next. It's the universe keeping its secrets. But this creates a huge problem for computers.
And that problem? Well, it really came to a head back in the 1940s with one of the world's very first supercomputers, the ENIAC, and a project that had stakes that were, well, about as high as they get.
Okay, so picture this. It's 1946. The legendary mathematician John von Neumann is deep into calculations for the hydrogen bomb. These complex simulations needed a steady stream of random numbers to model the totally unpredictable physics of a nuclear reaction. The problem? The ENIAC computer had almost no memory. He couldn't just feed it a giant list of truly random numbers he'd collected from the real world. There was literally nowhere to put them.
And this gets us right to the core conflict. Machines, by their very nature, are deterministic. They follow instructions perfectly. You give them the same input, you get the exact same output every single time. They're predictable. But von Neumann needed the complete opposite, something unpredictable. He was asking the machine to do something it just wasn't designed to do.
So what do? Well, if you're John von Neumann, you invent a clever trick. He came up with a simple but frankly ingenious little algorithm to mechanically fake the appearance of randomness.
It's called the middle squares method. Okay, here's how it works. First, you start with one genuinely random number. We call this the seed. Let's just say our seed is 5555. Step 1, you square it, which gives you 30,858,025. Step 2, you just grab the digits from the middle, in this case, 8580. That becomes your first random number. And here's the magic trick. You then use that number, 8580, as the new seed, and you do the whole thing all over again.
And just like that, the pseudo-random number generator, or PRNG, was born. It spits out a sequence of numbers that absolutely looks random, but, and this is the big catch, it is 100% determined by that initial seed. If you and I start with the same seed, we will generate the exact same random sequence, every single time. It's an illusion of randomness, a totally predictable process wearing a clever disguise.
So, okay, how different are these two types of sequences really? I mean, at first glance, they can look pretty similar, but if you watch long enough, the illusion starts to completely fall apart.
This is the fatal flaw, the ghost in the machine. Because the whole thing is just a mechanical process using a seed of a fixed size, it is mathematically guaranteed to eventually spit out a number it's already seen before. And the second that happens, the entire sequence starts over in a perfect, predictable loop.
And the length of that unique sequence, right before it starts repeating, that's called the period. And how long the period is strictly limited by the size of that first seed you started with. This is where the difference between true and fake randomness just becomes crystal clear.
Think about it. If your seed is only 2 digits long, there are only 100 possibilities, from 00 to 99. So your random-looking sequence can't possibly go on for more than 100 numbers before it's forced to repeat itself.
You increase that seed to 4 digits, sure, you get a much longer runway, up to 10,000 numbers before it cycles back. It's better, but it's still finite. It's still ultimately predictable. The scale of this difference is just staggering. A 4-digit seed gives you only 10,000 possible starting points, which means only 10,000 possible random sequences can ever be created. And that sounds like a lot until you realize that the number of truly random sequences is, for all practical purposes, infinite. It's like the difference between a library that has 10,000 books and a library that contains every book that could ever possibly be written. It's not even a fair fight.
So all of this leads to a gigantic question. If these computer-generated sequences are predictable and we know they eventually repeat, how on earth can we use them for things like encryption and security?
Right? I mean, it seems like a massive vulnerability. If some attacker knows you're using one of these pseudo-random generators, couldn't they just try every single possible seed until they find yours and then replicate your entire random sequence?
Well, the answer lies in changing our thinking from perfectly secure to practically secure. And this bike lock analogy is just perfect. Is your bike lock unbreakable? Of course not. Someone with enough time and patience could sit there and try every single combination until it clicks open. But you still lock your bike because you're banking on the fact that it would take them hours, maybe even days, to do that. It's just not practical.
We use that exact same logic for computer security, just on a scale that's almost impossible to imagine. Modern systems use seeds that are so enormous that trying every single one, even with the fastest supercomputers on the planet, would take hundreds, if not thousands of years. It's theoretically possible to crack, sure, but it is practically impossible.
So the bottom line is this: security in this world isn't about being impossible to break, it's about being way too expensive and time-consuming to even try. That's the whole game of practical security. And of course, it's a constant arms race. As our computers get faster and can try more seeds per second, the seeds we use for our encryption have to get bigger and bigger just to stay ahead.
But for all its predictability, this system has one killer advantage. Imagine you and I need to communicate securely. Instead of us having to share a gigantic, multi-gigabyte list of truly random numbers, we only need to secretly share one tiny little random seed. From that one small key, both of our computers can generate the exact same massive random-looking sequence to scramble and unscramble our messages. It is incredibly efficient.
And that very efficiency leaves us with one last, really fascinating question. This whole system, this entire foundation of modern security, it all hinges on two people being able to secretly share that one initial seed. But in our world, where we're on opposite sides of the planet and can never actually meet, how do you securely share the one secret that's used to create all the other secrets? Well, that's a puzzle for another day.